Step ahead of the world.
Yeah.
Okay, let's get started. So today is about random oracles or no random oracles. So Gal will get us started about talking about recent attacks and some potential defenses. And hopefully if you are sufficiently scared about using random oracles, the rest of the day will be about SNARKs without random oracles.
Thanks, Abhishek. So I'll be talking about Fiat-Shamir and this mitigation, trying to mitigate an attack that recently occurred. This is joint work with Arnon. So in this talk, I'll always be focusing just on Sigma protocols. So these are 3-message protocols, and they're public coin, which means that all of the verifier's messages are uniformly random. And I'm also going to be in a pre-processing model so I'm going to talk about only Sigma protocols for circuit satisfiability. So the prover is claiming some circuit, that it knows some witness for a circuit that is equal to some y. And the verifier is allowed to get some digest of the circuit. This doesn't necessarily have to be something cryptographic. This could also just be like a Turing machine if the circuit is uniform or something like that. I'm just thinking of allowing this model. This is usually what we want in SNARKs. So I said it's 3 messages. So we have the prover sends some M1. Then the verifier chooses its random message. And the prover answers with some M2. And then the verifier takes a look at everything that it can see and decides whether to accept or reject. This is a Sigma protocol, and I'm going to only focus on Sigma protocols in this talk. So importantly, we have 2 different notions of soundness. The first is statistical soundness, which I'll call a proof, which is soundness against unbounded provers. And the second is computational soundness, which I'll call an argument, which is against polynomially bounded adversaries. Okay. So we have Sigma protocols. They're nice, but they're interactive. So along came Fiat and Shamir and said, let's try to remove this interaction. Their idea is basically to say, the whole soundness notion in the interactive proof occurs because the prover doesn't know the verifier's message in advance. So let's try to replace its message by the output of some function that is very hard to predict. So what functions are hard to predict? Intuitively, a hash function is very hard to predict. So we're replacing the verifier's message by a hash function in the following way. The prover chooses M1. Then we hash all of the things that the verifier would see up to now, up to the first message, which is the digest, y, which is the output of the circuit, and M1. We derive the randomness this way. And then the prover will derive its message based on this randomness, send M1 and M2 together. So now it's non-interactive. And the verifier can also derive this message row based on the same things that the prover did and decide whether to accept or reject based on that. And also notice this is very nice. If M1 and M2 are short, then this is succinct, and this is why this thing is used a lot for building SNARKs. And actually, to wake everyone up, I have a debate I want to settle. Do we say succinct or succinct? Let's just vote. Who says succinct? Okay, and succinct? Moni raised his hand twice, which I guess is the right answer. This is not related at all to my talk, but I just wanted to, I think more people lifted their hands for succinct, by the way.
How many native speakers?
It doesnn't matter. It's
however it was pronounced before, it's now going to be.
What is the digest?
What's the digest? So it could be some cryptographic thing. So it could be some, or it could even, like in the case of GKR, it could be Turing machines that represent the circuit. So there, it's a log space uniform Turing machine. I'm not really going to focus on what the digest is. This is just sort of the form, but this allows the verifier to run in time that is smaller than the circuit. And usually this is something that we want, so I'm just allowing this in the model. Any more questions? Okay. So because of all these nice properties, because of non-interaction, this is Fiat-Shamir heuristic is widely deployed in real-world crypto systems, not just in SNARKs, also in digital signatures and way beyond. I will just mention that, so I gave this talk in front of Adi, and he kept complaining every time I said Fiat-Shamir. He said, this is not Fiat-Shamir, this is not Fiat-Shamir. And he's right, they proposed this, this heuristic for a very specific, turning a very specific identification scheme into a signature scheme. And in his, he thinks that this is Fiat-Shamir. You know, we've been abusing the name. So every time I say Fiat-Shamir, actually it's Fiat-Shamir star, so that, you know, to keep Adi happy.
So who is the first one who proposed the general version of Fiat-Shamir?
Mikali, I think.
I'm not.
I mean, Mikali for, I don't know, he said let's use that for Killian.
No, no.
Schnorr protocol before Mikali.
Oh.
They used that way.
Yeah,
Schnorr
Schnorr
for sure.
used this, but
You just
but
get
in the
to-
very general sense of this, I'm not really sure.
I can take credit.
So it's not Pierre. Okay. So you know, we have this this heuristic. It's very nice, but is it secure? You know, just this idea makes sense, but sure, we have to prove something. Fiat and Shamir didn't really, but Poincheval and Stern did prove that this is secure in the random oracle model, meaning that the hash function is modeled as a completely random function. And this is true for both proofs and arguments. For Sigma protocols, this is just true. For multiple rounds, you will have to have some like round-by-round soundness or state restoration soundness, but these properties are true for natural protocols. But again, I'm mostly talking about Sigma protocols here. So for proofs, Alex talked about this on Monday. There exists, you know, assuming enough crypto, there exists hash functions for which the Fiat-Shamir heuristic is secure, and there's a lot of work on this. There's still ongoing work on this. But pretty much, we believe that the Fiat-Shamir heuristic should be secure for proof systems, so for statistically sound proofs. But for arguments, there's a line of attacks showing white box or diagonalization techniques that break Fiat-Shamir. And what do I mean by this? I mean an interactive protocol, which is secure as a Sigma protocol or as an interactive protocol, but it's insecure after making it non-interactive for any concrete hash function. So there's no, we're not going to be able to prove anything, any hash function with any property that will be secure. This is when we actually instantiate it concretely. So examples of these attacks. So actually, Barak's protocol is already an attack on Fiat-Shamir. It's not a Sigma protocol. It's not an identification scheme. And so Goldwasser and Kalai showed that this can be adapted into an identification scheme, sort of contrived identification scheme, which breaks if you try to make it non-interactive. This other work by Bartuszek, Bronfman, Holmgren, Ma, and Rothblum, they were looking specifically at the like Killian-Mikali style proofs, which were talked about extensively, I think, on Monday. So they showed actually two sort of attacks. One is a PCP, where if you apply this PCP to the Killian transformation or Killian-Mikali transformation, it becomes insecure once you do Fiat-Shamir. The second attack is sort of they build a collision-resistant hash function. Remember, you need a Merkle tree for you take the PCP, you commit it in a Merkle tree in Killian's protocol. So you use a hash function for that, a CRH for that. So they took a CRH that sort of is aware of the Fiat-Shamir hash function, and with this CRH, which is an actual CRH, it still breaks Fiat-Shamir. So it's a slightly different, it's a different style of attack from the other three. And we have this recent attack by Ron and the guys from Ethereum, whose names I keep forgetting, so sorry. What?
They're Russian.
Yes, yes. Thank you. Thanks, Leo. While these were contrived and seen as contrived, this KRS attack is a direct attack on a natural variant of the GKR protocol. and again, I've given this talk in front of Guy, and he says, no, this is not GKR. Again, variant, so GKR star. If I say GKR, I mean GKR star. And this is an actual protocol that was deployed in practice, and they actually had to do some fix to not allow this kind of attack. And so I gave a similar talk recently at Simon's, and when I gave this, Ron Kennedy noted that I'm part of the problem. He said it in a nicer way, but I'm part of the problem by calling these things contrived. So the thing is that, I mean, it turns out they're not that contrived because this attack, is very similar to these attacks, but because we sort of as a community, we keep thinking of this as contrived attacks. We keep saying they're contrived attacks. We sort of have been ignoring them in some sense.
So the word contrived has a meaning, right? It's designed for a certain purpose. So with respect to this
it's
meaning,
true in that
quite
sense,
accurate.
but we tend to attach to it the meaning that it's not going to occur, which is probably so. The message of this new work is, I guess, twofold. One, for the practitioners, that they should actually know the literature. They should know that there are attacks there that could be used, which is this protocol. They weren't aware of this attack, and for us, that we shouldn't think of things that are contrived necessarily as things that cannot occur. We should be very careful about when we say this. So let's be careful when we say contrived to make it very clear what we mean. Otherwise, Ron will be sad. So let's not do that. I will mention that we don't have any attacks on things like Schnorr's protocol or the Fiat-Shamir identification scheme or digital signature. These seem to be because in all of these attacks, we sort of need to be able to compute arbitrary functionalities. Arbitrary computation. And Schnorr's protocol doesn't seem to really allow anything like that. You just are working over a group. I will just say that I sort of do conjecture that there is some kind of an attack on Schnorr's protocol that's similar to the CRH attack, where if you use you might be able to take a group that has where discrete log is hard, and somehow like put into it the Fiat-Shamir hash function. And it would still be secure in the sense of discrete log, but that might break Fiat-Shamir. This would actually sort of be contrived in the sense that I said not to do, but yes.
What do you mean again when you say it supports arbitrary computation? Do you just mean you can pick the input and it needs to support that input, therefore there exists like an attack?
So we will see how these attacks look. I hopefully we'll get clearer in a moment. But so we're using the fact that, so we looked at circuit satisfiability. We're using the fact that we're sort of using Fiat-Shamir on something that's proving general circuit satisfiability or general like computation, basically ones that are strong enough to compute the hash function themselves. Whereas something like Schnorr's protocol doesn't seem to be doing any computation, right? You're not really proving a computation.
You could prove R1CS with Schnorr, no?
Just Schnorr by itself.
No,
nothing on top.
no, not, you would
Only Schnorr's
like,
protocol.
Yeah. Okay, so what are our results? We have a new transformation that we call XFS, Extended Fiat-Shamir, and it's aimed at mitigating these white box attacks. Our focus is on practicality, so we want negligible overhead for the prover and the verifier. We would like it to circumvent the recent attack on the GKR protocol. There are some caveats to this. We only work for Sigma protocols. The GKR attack is multiple rounds. Also, we don't really know how to. The attack doesn't seem to work if you have what we did, but we have to put this caveat. And we have some evidence for security. We proved that XFS is secure in a relativized model where Fiat-Shamir is insecure. So while we can't prove anything in the standard model, we don't know how to prove anything in the standard model, we still can show that at least Fiat-Shamir is not secure and ours is secure in some model. And we don't defend against everything. So in particular, we don't really defend against, so in Barak's protocol and in Gvaludasser-Kalai, you're able to have arbitrary polynomial computation in the sense that it's a Turing machine. So you don't know the running time in advance. You just, this is actually really important in Barak's protocol specifically. Yes?
When you say don't defend, what do you mean? Do you mean there's an
What I
attack,
mean is, okay.
the model doesn't capture it?
This model doesn't capture it, yes. And also, conceptually, we sort of don't capture it. We'll see in a moment that we sort of use a proof of work that is harder than the hash function, or harder, sorry, than the circuit computation. And if you don't have a bound at the beginning, if you don't have an initial bound on the size.
So there is an attack.
If you use a Turing machine instead of a circuit, then there's an attack. Turing machine where also you sort of like hide the length of the computation with the sort of like what Barak does. That does attack, yes. We would hope to get something that also manages to get around this. And it seems also that this attack with the CRH also it's not in this model, so we don't know how to prove anything about its security. Basically, the CRH is sort of computing a SNARK on the hash function, and this sort of seems very powerful, and we also don't secure against that. So it's, we've secured against this attacks that sort of look like the GKR attack in some sense, but not all attacks. It's still open. Are there any questions about this?
So do you have a characterization of the new attack of Arnon et al.? And then you're saying that the characterization is captured by the relativized model?
Roughly, yes. It's not exactly the GKR.
From my understanding, for two reasons, our attack is not captured by your model, right?
Yes, because first of all, it's multi-round, and we're only talking about signal protocols at the moment. And also, this model, in this model, so succinct proofs, they don't exist in this model. So you can't have succinctness in this model. And so GKR is succinct. It basically has to, if you were to try to plug in a hash function, okay, I'll go into the model a bit later. But basically, it doesn't directly capture their protocol. And it seems hard to model exactly their protocol without actually going to the standard model. But it gives some evidence. So if you sort of believe that the GKR part of the protocol is like split into two parts, the commitment and then the GKR part, if you sort of believe that the GKR part is secure in some sense, which I can't really define, then it seems to you can sort of go to a hybrid where you are in this model. Does that sort of answer your question?
Sort of answers, just feels the statement is a bit vague. I don't quite know how to precisely interpret.
We will see the somewhat more formal things. We'll also see the attack, and then, but again, we don't fully protect against their, like we can't provably protect against their attack. But again, everything here is sort of heuristic in the Fiat-Shamir for arguments world. Any more questions? Okay. So I'm going to describe a toy protocol. It's not necessarily the simplest protocol to show this attack, but it's sort of formulated in a way that makes sense for, especially for the GKR attack and for how these things might be used in practice. So what is the protocol? So we have a commitment. We have a succinct commitment scheme. And we want a prover that proves that it knows W such that C of W is equal to Y. It's going to be a very stupid protocol. So first of all, the verifier gets a commitment to the circuit. The prover is going to send a commitment to the witness. And the verifier then chooses some randomness. And the prover is just going to decommit the circuit, right, and the witness. By this, I mean it sends C of W and proves that they're actually in the commitment. Fine. Now the verifier, after it verifies these commitments, I just didn't write this because it's just too much text. It checks whether this statement is true, right? This is sort of what it's supposed to do. Or it checks this weird claim that the circuit on W is equal to 1 concatenated by the randomness that it chose. So I'm installing a trapdoor. This is what the verifier sort of should be doing, but it's actually also checking some very stupid trapdoor. So first of all, this protocol is complete, right? This if C of W equals Y, then the verifier will accept because it'll just see this. All right, so it's fine. Why is this sound? Well, this follows from it's computationally sound. It follows from the commitment scheme. If the commitment scheme is binding, then the prover can't open something that it didn't commit to. So it committed to some C and some W, then rho was chosen. So first of all, okay, what does it mean that we're in soundness? It means that there's no W, or that so that C of W is equal to Y, or the prover does not know a W, so it couldn't commit to one. Therefore, this statement will be false. So the only way to attack it is this statement, but rho was chosen after W and C were committed to, and the decommitment holds. Yes, Tama.
I guess still not relevant, but are you talking about adaptive stuff? Like, does the prover get to choose C?
Yes, the prover is choosing C, yes. Sorry if that wasn't clear. The prover will be able to choose C as well. C chooses C, W, C and Y. And I guess it chooses W as well by M1 in this protocol. Yeah. So it cannot predict because the prover cannot predict rho, committing to C and W will not be able to output one concatenated by rho with, except for negligible probability. So this is sound, right?
Sorry, what is the role of the input to the verifier?
The input to the verifier, you mean this?
Commitment to C, yeah. This is
It's not really doing anything. It's just, this is just a toy problem. Everything in this protocol is pretty stupid. But we'll use this in the attack. We'll use this thing in the attack.
But in terms of statement, what does the verifier know? So because the statement is I know W such that C of W is equal to Y, so the verifier gets Y ahead of time as well.
Yes, yeah, sorry. It also gets Y and it gets this. I should add that this. Yeah, the verifier gets.
But
Y.
everything he knows about C is commit, so he doesn't know anything more than the.
Yes, at this point, but obviously here it gets the decommitment, so it does learn that. Okay, so now let's look at Fiat-Shamir version of this. So we have some hash function H. And the prover sends M1 and M2. M2 was the decommitment. So M1 is the commitment to some W, and then you have the decommitment to this W and C. Now, what does the verifier do? Well, it does the same check that it did before, and also computes rho as the hash function, as the output of the hash function. Okay, and I claim this is insecure for any H. So what I mean again? For any H, there's a prover strategy, which in this case is just specifying the circuit, specifying the output, and specifying the witness. I say the witness and not M1 because we have a commitment to the witness, and you have to open it. So I'm not going to try to break the binding of the commitment scheme. So I just need to specify W, such that, first of all, this is to be a no instance. So for all W prime, C of W prime is not equal to Y. So it's going to be a no instance. But the verifier is going to accept it. Is this clear before I show the actual attack? This is probably going to be the hardest slide in the talk, just because there's going to be diagonalization. It's not actually complicated. It's just going to be very hard to parse. Yes, yeah. So what is the circuit? The circuit is going to get W, and it's going to parse it as the digest. So this is the digest concatenated by Y. It's then going to compute the commitment. It's going to compute M1. And then it outputs 1 concatenated by H of the stuff, the same stuff that's computed here. So I've given you the circuit. It's still not clear why this is an attack, but then we set Y to be the all zero string. M is just the output size of this thing here. Then psi is going to be this commitment, just like it is here. And we set W to be exactly what you would expect based on this parsing, which is just psi, the digest concatenated by the output, right? OK, so now sort of slowly, why is this an attack? First of all, why is it a no instance? This is not hard to see. Y starts with 0, and the output always starts with 1, no matter what witness I give it. Therefore, it's a no instance, right? There's no W such that C of W is equal to, starts with 0, but the claim is that something that starts with 0. And now, why does the verifier accept? Well, we look at C of W. C of W takes in this and outputs this. So it outputs 1 concatenated by H of psi, y, and M1. M1 is computed exactly like this. So it's exactly this M1. And so we have 1 concatenated by rho. And so the verifier accepts because this is actually the output of the circuit. I'll go through it again, just because this diagonalization stuff, at least for me, it's very confusing. So the circuit computes, it gets the witness. This is the same witness that the prover has committed to. It commits to it just like the prover does. And then it outputs, then it has all of the transcript that the verifier has at this point. It can compute this hash, and it outputs 1 concatenated. But it has this 1 is only to do this thing, so you can sort of ignore that in the verifier accepting part. And the point is that there's some diagonalization going on. There's this psi, the circuit is getting its own digest, and it's also able to compute M1. So it's basically able to compute the hash function, or the next message function by itself. Is this clear? This is the point of the proof. Yes?
Sorry, can you repeat why is rho the hash?
Yeah, so by definition on the verifier side, rho is the hash of psi, y, and M1. Psi and y are just specified by the outside here. And M1 is the commitment of W. And this is the same thing that the circuit computes. It computes the commitment of W in exactly the same way. Yes, Tom?
Is there no circularity? Like, psi is defined by C, and C is psi.
There is circularity. That's why this isn't. This is diagonalization.
But I was asking whether it's well defined.
Oh.
I got my.
Oh, okay. Yeah, it is well defined. Okay, so really the problem is that the verifier.
Sorry, just
yes.
1 second.
Sorry.
This commitment is a small commitment, right?
Yes. So these are succinct commitments. M1 and psi are succinct. That, I specified. Maybe I didn't say this clearly enough, but in the previous slide I should have specified that the commitment is succinct. Yes. Or succinct. Yeah.
And like where we're using that this is an argument and not a proof is like because in the proof setting you would get the circuit C instead of the commitment to it. Is that where it breaks down? If
yes. So I will mention that there is a version of this attack that works for proofs, and it's sort of you can see it as an attack on CI hashing, which actually Alex mentioned, I think Alex mentioned it on Monday. I'm sort of just putting it in this form because this is sort of how this would be used in a system. This is how this was used in the GKR attack. But there's also a way to view this as an attack on CI hashing. Like where the relation can sort of compute the hash itself.
That's really the original CGH attack.
Yeah. Were there questions?
So is it just fair to say that this is diagonalization in this pre-processed model where the circuit is hashed in advance? Is that the whole point? Like that basically without the digest, this wouldn't work, right?
Without the digest, this wouldn't work unless you sort of have yeah, I guess yes. I think it wouldn't work.
So does this only work for the adaptive?
Yes, so this is adaptive soundness. The hash is chosen in advance, and then the circuit, then the prover chooses C. Yeah.
So can you explain again what's the role of the digest in that attack?
So in this attack, this specific attack, the digest is just a way to have the circuit get its own input. If it has some small description, it doesn't necessarily need to be a commitment, but it needs to have some small description, and then it can get itself. So this might also not be, in this example, it's a commitment. It doesn't actually have to be a commitment. It could, if everything is like a log space uniform, you could also do this kind of attack in that way. Does that sort of make sense? Okay, so the problem is that the circuit is able to compute the verifier next message function, because now it's a deterministic function based on the hash function, this is really where the attack is lying. And the naive solution is to just make the hash function more complex than the circuit. And this, it's a reasonable solution. It does have a few downsides. First of all, the verifier needs to compute the hash function. Now, once you make the hash function sort of more complex than the circuit, this means that the verifier has to be more complex than the circuit in this same sense. So this means that we have to inherently have a slow verifier, and it's sort of non-compatible with recursion. If we want to prove claims about the verifier, then we're sort of stuck with verifiers of the same size, at least as long as we're using the same proof system. And also, just saying this, it's not clear why this would be secure. Like, there's no argument about security here. I mean, it makes sense, but you have to be very careful about what you mean. So we propose an alternative solution, which is the idea is still similar to the naive solution of making H more complex, but we use a proof of work to make the next message function more complex than the circuit, but easy to verify on the side of the verifier. So it's sort of asymmetrical now. So it's similar to this idea still, but asymmetrical. Also, we tried to prove something about security. Was there a question?
So more complex, you mean longer?
It depends on exactly how the attack was launched. Yes, in this example that we saw, I mean longer, so more time. But for example, in the GKR attack, actually it seems that more depth would probably be enough, because in GKR you're sort of proving low depth circuits, and then if your hash function takes more depth than the circuit is allowed then to compute, then it sort of can't compute the circuit.
So the idea is, like, let's say, would not be able to input.
It wouldn't be able to compute this thing, which is required to compute rho.
Oh, because it's too hard. Okay.
Because it's too hard.
Okay.
Yes.
And
Because
that
it's
was
too
what
hard,
was
not because it's too
also,
long. Okay.
that's what was implemented in practice.
Yes, that was what it was. That's a good point, Ron. In practice, they just made the hash function like deeper, and so in GKR, the GKR attack, that's how they circumvented this.
So this means that, like, for complex circuits, you're gonna need like super complex hashes. Right? Like,
You're probably
Yeah,
not going to
but
prove
that's why we
complex.
have we're gonna.
The point
have
is that
a
you're
proof of-
proving an NP statement. So you're going to anyway, you don't want complex circuits to begin with. You want to sort of flatten it, like the Cook-Levin style thing. So it's not really targeting very complex circuits. You want to simplify the circuit so you can prove anyhow for efficiency reasons.
Gali, the technical level, is this the same use of proof of work that is used in systems like SNARK to make
No, we're going to see what exactly I mean by proof of work. It's similar, but it's not exactly this proof of work. Yeah.
So would the attack still work with like salting? So basically the more that you fix your application, and then, I mean, the salt is chosen, let's say, randomly, maybe, and then you kind of do your Fiat-Shamir. But the hash function is, let's say, prefix, or is a prefix, or I guess suffix, whatever, applies the salt to the hash function.
As long as the prover knows the salt in advance, it could, and it chose the circuit. So it depends on the adaptivity. If the salt is chosen after the circuit, this attack probably might not work. Probably won't work.
So in general,
but if the salt is chosen before the circuit, if there's still adaptivity, then it's might as well just be part of the.
Well, you can make it very long, right? So can you make it long that it doesn't longer than the input of the circuit?
Longer than the input of the circuit. Yeah, that's just making it harder.
I mean,
more
it will make
complex.
the computation deep in some sense, indirectly.
Yeah. Then the verifier has to compute that as well.
Yeah.
If you can add to Evgeny's question, 2 points. So in the paper, we also have some versions of that type that are kind of somewhat non-adaptive, so they would not depend on the salt. That's one thing. But the other thing I want to say is that in practice, you really do want your circuits to depend on the salt. If you're doing stuff like recursive composition, you do actually want to prove stuff about the underlying hash.
Yeah. Okay. So what is this transformation? First of all, I want to define proof of work, which I promised Yuval. So in this model, we have a hardness parameter L, which is, you can think of as much smaller than 2 to the lambda for some security parameter lambda. we have two algorithms: solve, which gets a puzzle Z and solves it in time L, and check, which gets a puzzle and a solution, or claimed solution, and verifies this solution. And what we want is negligible in lambda security, so negligible probability of outputting a correct solution in time much smaller than L, but if you have preprocessing. So what I mean is, so you have maybe the public parameters are chosen, then you have some preprocessing algorithm that runs in time much larger than L. It outputs some auxiliary information, and then the puzzle is chosen. After this, there's a algorithm that tries to solve this problem given the auxiliary information, given the puzzle, in time much less than L, and it outputs a claimed solution. So this should fail with high probability. Okay, so this is our proof of work. Why is this different from something like the Bitcoin proof of work? Well, the Bitcoin proof of work, they're guessing a solution works with probability 1 over L. So they're like the security parameter and the hardness parameter are sort of tied together. And here we sort of really want negligible probability in the of succeeding in cheating. And this is, by the way, implied by proofs of sequential work. So these are stronger than these strong proof of work. It seems to be somewhere in the middle. And we have two constructions of strong proof of work. Hopefully we'll see one later if we have time. I don't think we will, but we'll see. Yep. Well, it also needs to be hard. You also need some hardness. It's not just the verification. Or yeah, this is the hardness, right? This is saying that we're going to attach this to the hash function in some sense, and then this is going to say that it should be hard to compute the hash.
But I think Tom was saying generally if you had a hash function that is somewhat hard to compute,
oh yes,
easy to verify.
If you have a hash function that's somewhat hard to compute and is easy to verify, then it already sort of inherently has a proof of work in this sense. What?
Hard to compute for the verifier, I assume.
Hard to compute for
Hard to compute for everyone, for the circuit especially. I really want it for the circuit.
But you still want the proof, right?
Yes, yeah.
So somewhat hard.
So somewhat hard, yeah.
So if you have like time lock puzzles and you have proofs of work, it's somewhere in the middle, right? It has to be hard to compute. It has to be easier to open.
Yeah, to verify.
Right, easier to verify. Okay.
Yeah.
So there's also a question of verification
versus
actually computing. Okay.
Yeah.
The big difference is that it's sort of a guaranteed amount of work versus for proof of work it's an expected amount of work, no?
Here it's an expected amount of work, whereas for us it's guaranteed.
Yeah, for strong proof of work?
Yes, yeah.
It's a guaranteed amount of work?
Yes. Yeah.
Versus for
well, okay,
proof of work,
it's not okay.
expected amount of work?
It's not okay. Sorry, I misspoke. I don't require a guaranteed amount of work. We have two constructions. One has a guaranteed amount of work, and one is expected. But the probability, if you're like far from this, should be negligible.
Ah, okay. Like you just want a very tight concentration.
Yes, yeah, we want a very tight concentration. Exactly. So now I can specify the actual transformation. So prover starts off with computing M1, and now, differently from what it had before, it computes a puzzle based on the hash function on what the verifier has seen up to now. So sorry, of psi, y, and M1. So it computes a puzzle, and then solves this puzzle immediately. And then it plugs the solution into the hash function again with psi, y, and M1 to compute the next message function. And then it computes M2 based on this verifier message. Then it can send over M1 and M2, but it also sends over the solution. So we also really want a solution that's short for this. Now the verifier can compute the puzzle. This is sort of how it computed the randomness in the regular Fiat-Shamir. And then it can also compute the row given the solution, because it has the solution. Then it can check whether the original verifier would have accepted. And it also verifies that the proof of work is actually valid. This is our transformation. So it's making the hash function harder, this hash function harder, the one that computes row, by adding this proof of work, which is going to be checked by the verifier. So let's see what happens with XFS in the toy problem. So this is, again, the toy problem. And we have the Fiat-Shamir hash function. Now we're going to do XFS. So the prover has to send in M1 and the solution. And also this is M2, the decommitment. The verifier is going to compute Z, compute rho, just like I said before. And now it checks, this is the check that I did before, right? This was the sort of honest check, and this was the trapdoor. And it also checks the proof of work. So let's try to launch the same attack. So does this work on XFS? We want the circuit to compute rho in this attack, right? So trying to launch this attack would sort of look like this. So C of W parses W as psi and Y. This is sort of like we had before. It would compute the commitment. And then we'll just add to compute the hash function, the proof of work inside, which is computing, getting Z and solving the puzzle. And then it could output 1 concatenated by H of all of these things, which is exactly what the verifier does here. So this is just trying to do exactly the same attack and plugging it in, saying, oh, the verifier next message function is slightly more complicated now. Let's just mimic that. So the way to counter this is to set the proof of work hardness to be larger than the size of the circuit. So now the circuit can't compute solve. So we can't do this. This is now impossible for the circuit to do. Right? So once we set this proof of work to be hard enough, the circuit cannot compute this S, and so this kind of attack doesn't work. But actually, this is a bit more subtle, because the circuit is not just a circuit, it also receives some input that's actually sort of chosen by the prover, right? This is W is chosen by the prover. So the question is, can there be some W that helps solve this puzzle faster? And this is where we use the preprocessing. So the puzzle Z is computed after the circuit and W are committed, right? Because C and W are committed, and then Z is equal to something that depends on their commitment. And C and W cannot help, therefore, because they were chosen before they knew the puzzle, they can't help solve the puzzle faster than time L, which is, again, hard, since this would invalidate the preprocessing security. Does that make sense?
You critically assume that C is a circuit and not a Turing machine.
Yes, exactly. This is why we can't protect against arbitrary computation Turing machines, because I wouldn't, well, I can in some sense, in the sense that I set the proof of work to be super polynomial, but then the honest verifier is working in super polynomial time, which doesn't make sense anymore.
And can you do the same trick using proof of memory, proof of state, and assume that instead of a circuit being bounded size, that it's a polytime machine but has a bounded space complexity? Right? Because there are some applications where you have limited space.
Yeah, potentially yes. I haven't thought about that, but it seems like it should work. It seems that as long as this proof of work is for whatever hardness parameter, you can sort of claim that that doesn't allow this diagonalization. It should work. Right? Yeah.
And so along the same lines, if instead of the proof of work, you would use the proof of sequential work, as you mentioned before.
Yeah. So proof of sequential work is stronger than our proof of work. And
then the circuit would be arbitrarily big as long as the depth is kind of smaller than the proof.
I'd have to think about that. Sorry.
So, if I understand correctly, I want to make sure that circuit C cannot compute the entire message from prover to the verifier. So what if I just say M1 is the commitment to the computation tableau of C of W without the proof of work, and for the C to compute its own computation tableau, that would be not possible because it's a circuit.
So this kind of thing seems to be where the problem lies in like the GKR attack, is that sort of they don't do that, and other protocols sort of do that. you wouldn't just be able. Okay, in this specific problem, if you open that up, then that's fine. But you would need for an actual protocol, you would need to prove that this is actually the trace of the computation. But like most protocols actually work that way, and it might work.
So then I will need to add an additional proof of work for those protocols that has the capability to prove the trace.
I'd have to think about it. I think you're right. We have some work on this in this direction, but actually defining this thing and showing whether this works is not trivial. So.
Okay. Sorry, could you maybe repeat the pre-processing security?
The pre-processing security says that if someone has a lot of time before the puzzle is chosen, and then gives some auxiliary information to the person trying to solve the puzzle, it shouldn't be able to solve the puzzle faster than L, even if it gets this information that was chosen again before the puzzle was chosen.
But this holds no matter how I choose the puzzle?
The puzzle is chosen randomly, so uniformly randomly, it's assuming this.
It's not uniformly randomly, it's like using
the hash. Yes. So there is a small thing that here is, yes, we are using the hash, whereas the definition used uniform randomness. I'm assuming that the proof of work is sort of very simple, in the same sense that like Schnorr is very simple, that it shouldn't be able to compute some like arbitrary computation. And we have examples of proofs of work, and so this seems like a reasonable assumption.
So it seems like definition-wise, you need something a bit stronger, right? Like you need something that relates to the way the hash is defined. Otherwise, like there could be a proof of work.
So I'm going to show some kind of proof in a random oracle model, and I'm going to leave it at that because we don't really know how to prove anything more than that. So I don't have much time, so I will talk about security now. So security of XFS, or going back to Alex's talk, how to provide some sense of hope. So what I'm going to talk about, yes?
So the way, just to understand how this toy protocol connects to the attack in ARS, so instead of this decommit C step, the rest is
you run GKR, yes. So this decommit C is actually run GKR. Yeah. So if you that's what I meant by like, if you sort of believe GKR is secure, then what is GKR doing? It's sort of running the circuit step by step, and then just sort of checking the output. So if you sort of believe that there's no attack in that place, then this sort of becomes the same protocol. Yeah. But this is like very hand-wavy and not a formal statement. Okay, so we're going to talk about the relativized model, which is so we have an ideal model with a random oracle, but we're going to give all parties this random oracle. So we have the sigma protocol, and the prover, the verifier, the circuit, and the digest, they all have access to this random oracle. This is what I call the relativized model, the relativized world. And this captures the insecurity of the toy problem, because basically if you go through everything that we did, the commitment could just use the hash function. You can think of a Merkle puzzle, Merkle tree, sorry. And the verifier only uses the hash function in a sort of black box way. The circuit also used the hash function in a black box way. So everything in the attack sort of holds in this model. So this toy problem works. Again, in this model, no succinct proofs exist, but this proof is just not succinct, and that's why it sort of makes sense. So what about XFS? Well, we show that in this relativized model, the XFS transformation has the following. So if you have a sigma protocol with some round-by-round knowledge error, and a strong proof of work with some error epsilon, then the non-interactive protocol has knowledge error k, which is bounded by t times the knowledge error plus t times the strong proof of work error, where t is the query complexity of the malicious prover. Remember, we're in an idealized model, so the prover is not bounded. It's only bounded by the number of queries it makes to this oracle. And so there's an XFS star here. This is a slight modification of the transformation that we already saw. I'll show this. But first, I want to just say a few words about the random oracle security for Fiat-Shamir. So the way it works, so again, now we're in regular Fiat-Shamir, no proof of work, no anything. How do we prove this? This is secure. How did Punch von Stearns prove this, at least in the modern notation for all this? You want to reduce this to the security of the Sigma protocol by taking any adversary for the argument and transforming it into an adversary for the Sigma protocol. And we're going to assume for simplicity that whenever the argument prover outputs its attack, so its attack, it's like C, Y, M1, and M2, then it must make the query psi, which is the digest of C, and Y and M1. So I'm just assuming this. Actually, if it doesn't make this, it's even easier to show. But I'm just going to assume this. So what we're going to want to do is sort of put in this verifier message as this query. The way we do it is, so this is how PSSP works. It simulates the argument prover up to the ith query, where I is some random is the random value. By simulate here, right, PARG has a random oracle, so I'm simulating this with just random answers. And then we hope that this ith query is this query that we have here, which is in the form psi, y, and m1. We can get out of, I'm assuming that you can get out of psi the circuit. And then you have y, and you send m1, right? You send m1 here, and this is how you chose the circuit. This is sort of c and y are sort of the claim, and m1 is the first message. Now you receive rho, and you keep simulating the argument prover with rho programmed instead of the hash function. So you just, when it makes this query, you answer with rho. You keep running it, and eventually you'll get m1 and m2. This is the m1 and m2 here, and so you can send this m2 as the answer. And the point is that the argument prover can't distinguish between like an actual random function and the programmed oracle with rho, because rho is random. This is just a random message. And so the prover convinces the verifier with the same probability. The prover here convinces the verifier the same probability as the original prover up to this query, because I had to guess the location of this query. Why does this not work in the relativized world? Well, really the problem is that the circuit, the digest, and the verifier, they all have access to the hash function. And now they can potentially depend on this thing. They can depend on this query. And they can distinguish. So I might have programmed something in the prover, but I can't claim that the verifier accepts with the same probability here, because everything sort of depends on the hash function. So for XFS, this is just XFS in the relativized world. It's a similar proof idea, except that we have 2 additional steps. The first step is saying that C and the digest, they should not be able to compute this query. Now we have the proof of work query here. And this is due to the proof of work. The proof is very similar to the proof idea is very similar to what we saw for the toy problem. And so we've sort of protected these 2 guys. And we also need to say that the verifier does not make this query, right? Because everyone has access to the hash function. This turns out to be a tiny bit of a problem, because the verifier is not protected by the proof of work, basically because the verifier's queries depend also on M2. So there's no like circularity problem which we had that could sort of protect the circuit and the digest. The way that we solve this is by sort of prefix avoiding padding, so that the verifier cannot compute rho. I will briefly mention what this is. So we want to prevent the verifier from making the query. And we have something called a padder. This padder is going to output a prefix tau deterministically in the random oracle model. And the security game is that we have some adversary that chooses a suffix gamma. And it later cannot make the verifier make the query tau. This is this tau prefix concatenated with gamma. And more pictorially, we have the adversary and the padder. They have access to the random oracle. The adversary will choose a suffix. The padder will then choose a prefix based on the suffix. Then the adversary chooses a message so that it's trying to get the verifier given this message to make this query. And it shouldn't succeed. This is what the padder is trying to do. That makes, oh, okay, thought there was a question. So just examples for padders, a very trivial padder is to just pad with something larger than the verifier. Obviously, the verifier cannot make a query that is larger than itself, the original verifier. So that sort of is a very easy solution. It might not be efficient because it causes the new verifier to run slower than the original one. So if the message is short, then something of the form h of VSP, comma, this suffix might work. You have to play around with it a little bit. Or in practice, you might just not need a padder at all if you're sort of convinced that there's no way for your verifier to actually accidentally make this query. Then you might be convinced that you don't need this. You have to be careful making some kind of this kind of assumption, but it might be reasonable because sort of I think a verifiers are something that should have had a lot of cryptanalysis done on them. So we should, yeah.
It's one algorithm. If you're trying to prove that this one algorithm does not
Yes.
take this one
Yeah,
theorem,
a specific algorithm. So this padder is for this specific verifier.
You do specific analysis protocol by protocol to say in this protocol there's no way this query
Yes.
could happen.
Yeah. Oh, yes. So you could want to say that in practice this just shouldn't happen. Yeah. You would want to do this one by one, but this thing just solves everything, right? Because yeah. So the actual transformation is very similar to what we had, except that now the the prover, after computing the solution, will ask the padder to output a prefix, and then it'll also put the prefix in. And the verifier can also compute this and put the prefix into this query. Now this verifier is not going to make this query, and so we can protect against that as well. So this is what the XFS star was. We don't have time, but I have a few slides on the proof of work construction. I will skip those. So as a summary, so we saw that Fiat-Shamir is insecure for arguments due to these diagonalization white box attacks. We propose the extended Fiat-Shamir protocol aimed to mitigate these attacks. We use this strong proof of work, and we have some heuristic proof of security in a relativized model. It's very much insufficient, but let's try to prove some better statements. But we don't really understand much about the arguments in general. Future work. So first of all, a multi-round version would be very nice. So we could claim something. It's pretty much it's not very clear how to generalize this. What the right way of generalizing this for multiple rounds is.
Generalizing what?
The XFS.
The transformation itself.
Yes, the transformation itself, because we're sort of protecting, sort of assume that the first round is like you can extract a witness from it, and this might not be true for a general multi-round protocol. So understanding sort of what we should do is a question. Like for specific protocols like the GKR one that you had the attack on, XFS should probably sort of work. Again, you have the succinctness stuff that we can't really handle in any relativized model.
That's in terms of the analysis, in terms of like the, no.
Yeah, in terms of like,
Defending against it.
in terms of what is right, I don't even know. Yeah. We might want to talk about security proofs in some algebraic models. So there are models in which there are relativized models, which the random oracle the oracle is not just the standard random oracle, in which succinct proofs do exist, and potentially attacks can be launched on regular Fiat-Shamir in those models, and maybe XFS would be secure in those models. I would conjecture that there is some way to do this, but I'm not sure. It's be interesting future work. So there's in the real world, when people use Fiat-Shamir, when they use hashing, they use sponges, not these like hashes that can sort of take arbitrary length. And it's not immediately clear that everything here makes sense in that model. So the Ale and Michele have some work on analyzing Fiat-Shamir with sponges. So analyzing XFS with sponges also would be interesting. Thinking about patterns, this concept may be interesting in other senses. Also, sort of defining it for some like non-contrived verifiers, and of course, the easiest open problem is solving Fiat-Shamir for arguments, just in general. Last of all, I want to advertise the book by Ale and Elon, which is not unpaid and unsolicited. I just think it's a very good resource for this kind of stuff. A lot of the proofs that we have are like based on the notation that they have. I think it's very useful also to give to students and stuff. Also, another open problem is to change this to paid, but that's it. Thank you. Yep.
So you have a proof that you can't have a succinct argument in the relativized model. Is that easy to show, or?
It's a paper by Z. Ale. Right? And Analysa. Sorry.
And intuitively, it's because like you can't use things like BCPs and stuff.
Yeah, intuitively, it's because you sort of, in order to do something succinct that sort of refers to the random oracle, you have to. I mean, in order to do anything that refers to random oracle, you sort of just have to send it over because you can't verify anything, so you can't compress it. That's in the intuition. Any more questions? Yeah, Ron.
I just wanted to suggest a small change to the last open problem. Instead of solve, I would say study.
Yes.
Solve seems to indicate that everything is fine, but I really think we should be studying also attacks, particularly against your mitigation and the one in our paper. I think it's really important.
So understanding everything to do with Fiat-Shamir for arguments, I think Ron's paper points out that we should, as a community, do a lot more work here. There's like everything basically is open. Ale told me to make jokes in the slides, and I realized I don't really need to because what we know about Fiat-Shamir for arguments is a joke, so that's already written in the slide. But yeah, this is just everyone start researching this. Any more?